This last homework is actually a really fun one, or at least it's designed to be a fun one. It's going to be posted on Blackboard, so you can all have a copy. I didn't bring copies today. But what it is, it's appreciating neuroscience in the movies. So your assignment is to watch one of a set of movies that we have listed. You are welcome to propose a movie of your own, and your TA and I will decide whether that's appropriate. But basically, you're going to write a short paper summarizing the movie and the plot, identifying the central neuroscience, neuropsychological, or neurological disorder that's treated in the film. And then the main part of your assignment is to go out and read some primary literature. This does not mean Wikipedia, okay? You must read things. You can read it, but that cannot be your only source, and you should have at least 2 other sources beyond Wikipedia to research what this disorder is really like and critique what the depiction was in the film. And then I asked for a bibliography of exactly the sources that you used. So it's a great way to, again, just get this appreciation of all the ways that neuroscience is depicted in the media. Get creative. I had a student last year, who wanted to do Passing Strange, you know, the Broadway show about schizophrenia. She used that as her assignment, and that was perfectly great. If you want to see a play or have another movie that's your favorite movie that you want to try and address, feel free to do that. But of course, you must get permission if you're going to use a movie that's not on this list. So look for both the new syllabus, the modified syllabus, and your movie assignment on Blackboard by this afternoon. Any questions about that? This is going to be due. Oh, there's also one additional component to the movie assignment, and that is there's going to be an in-class discussion of the movies that you chose and the kind of things that you found out, and that's going to be happening on December 7th. The homework itself is due in lab on that week. So not only be prepared to choose a movie and write up the report, but be prepared to discuss it both with me, but also in small groups in class on the 7th. Okay, great. And the last thing is that I've decided so I've invited. Everybody knows that they can email me to get to make an appointment to see me. I don't have set office hours because that has not worked very well in the past, but I decided to do a little modification, particularly for the preparation for the final. So I'm going to have established office hours for the 2.5 weeks leading up to the final, and I want to ask people that happen to be here today what your preference is. My suggestion is 2 out of the 3 possibilities. First possibility, Monday after class. Second possibility, Wednesday after class. That is 12:15 to, let's say, 1:15. I will be available. I may be able to have a room right down in our lab section, so it will be really easy just to come by and ask me questions. The third possibility is Friday afternoons. I know many of you who don't have classes. So, but I don't know what your class schedule is like. Maybe you're running off to class both Monday and Wednesday. Could I get a show of hands? Monday after class, useful or not useful? Okay, good, lots of hands. Wednesday after class, lots of hands. Friday afternoon, less hands. Okay, so I will, that's fine, I'm happy to do that. So I will announce it once I decide at what point I'm going to start doing this. But I invite you all. I'd love to talk to you about all aspects of the final. You should know that I'll be giving you specific indications of the major topics that we'll be covering on the cumulative part of the final. You know that the final is cumulative, as well as covering from the lecture starting today, right? So obviously we cover anything is possible from the lecture starting today to the last lecture, which is neurobiology of love. But the final also has this cumulative component that makes it more challenging. We will be specific about what we want to. We're not going to ask you minutia about, you know, tiny little details. We're still going to ask you about the main questions, receptive fields, basic neuroanatomy. So, but we'll give you a list of what we will focus on for the cumulative part of the final. All right, so I'm going to do Monday and Wednesday after class. Any other questions about homeworks, about finals, about midterms? Okay, great. So today we get to continue this small little snippet I started that last Monday before the exam, looking at learning and memory basic distinctions. And I just wanted to review, you had the exam in between, basic definitions, learning, learning is the process of acquiring new information. Memory is the ability to store and retrieve information. And the specific information is stored in the brain. So we've been talking about neuroplasticity. Can somebody give me an example of neuroplasticity, examples of neuroplasticity that we've talked about? Yes? Perfect. Musicians that have a larger cortex devoted to motor and sensory functions. Any other examples? Sorry? Heschel's gyrus for what? Yes, Heschel's gyrus. A non-musician example. We talked about several. Yes? The finger fusing study. Perfect. Okay, so these are all examples of how sensory and motor systems can change. But what we're starting is a whole section of the whole course devoted to one major aspect of neuroplasticity, learning and memory. You don't think about that all the time. So what is your name? Michelle. Okay. So Michelle's telling me her name right now. That means that in Monday's class, I'm going to remember Michelle. I'm going to remember her glasses. I'm going to remember what she looks like. And I would not be able to tell you what Michelle's name is. That means something has changed in my brain. And we're going to talk about exactly how that happens. That is a form of everyday plasticity that sometimes does not work very well. I'll be very embarrassed if I can't remember Michelle's name because I told you it right in front of everybody. It's been filmed and everything. So that gives me heightened motivation to learn Michelle's name. But everybody knows how well your memory works and how poorly it works. How many people couldn't remember something on the exam that they know they studied? Okay, so there you go. Hopefully, I'm sure it wasn't devastating for your scores, but everybody goes through that. There's a lot of material, there's interference, we're going to be talking about that, but I want you to appreciate this is a continuation of the discussion of neuroplasticity in a really, really big way. This is based on neuroplasticity. Okay, and I know we talked about this before, but I wanted to go into this experiment in a little bit more detail because it tells a story of experimental approaches and how you interpret data, but also how you could be wrong. So this is a story of Carl Lashley, a very famous psychologist who worked in the 1930s who wanted to figure out whether there was a specific brain area important for memory. And he tested rats' memory or a spatial maze. Seems reasonable. They're really good at doing spatial mazes. This is a top-down view of this kind of box maze. So the rat started here, and he had to learn to turn right and then left and then right and then left to get the food. And they got faster and faster and faster. And then after they learned this maze, and he got the time, how fast they are, because the rats always improved their quickness, why they were motivated. They were hungry, and they wanted to get this food. They did it really fast once they were learning their spatial outline or spatial orientation within this maze. After he did that, he did a series of lesions. And he focused on lesions of the outer covering of the brain, the cortex. And first he did systematic small lesions in lots of individual areas. He had a tool to do this. It happened to be a marble. So he used a marble, and he made lesions in the cortex of the rat. This was all under anesthesia. And he asked, did one area with my marble lesion cause any particularly severe memory impairment? That's all these individual tries of marbles all over the brain is what you see here. Here is the small percentage or smaller percentage of cerebral cortex removed and errors. The errors were not going up no matter where he lesioned in the cortex. Then he said, okay, I'm going to start lesioning more and more cortex. And as he lesioned more and more, then he started seeing errors during relearning. So he couldn't find a particular location. The biggest relationship seems to be the size of the lesion that is causing the most errors during surgery, the errors after surgery. So after surgery, they got these various sized lesions and various placed lesions, and they got put back in the maze, and their timing was tested again. So based on this data that he collected, quite a good experimental design, he proposed what he called the law of mass action. You need to know this law, and you need to know that Carl Lashley proposed it. The law of mass action says that the severity of the memory impairment for maze performance was correlated with the size of the cortical area removed. That is this relationship here. Bigger size, bigger errors. Not with the specific location. So does everybody get that? Does that make sense? Yes? Yes? Can I get some nods? Okay, good. So now I have a question for you. What would this graph look like if there was one part of the brain that caused severe memory impairment? What would that look like? Think about that. Yes?
It would kind of look the same because when you take out more cortex, you have a higher percentage of chance of taking out that single part.
Mm-hmm.
But some of the lower percentages would have taken out that little part that would way in there.
Perfect. So she said that likely part of this graph would be the same because when you damage cortex, you're damaging a whole big part of the brain. But some of these small dots down here where we tried different parts, it'd go up here, right? These dots, one of these dots would go up here. And that would mean I have a tiny little lesion, yet it caused a severe memory impairment. Where did I put that lesion? And that might be an area important for learning and memory. Okay, does everybody get that? Those are two possibilities. He did not see that in this experiment when he was lesioning the cortex, but that's what he might have seen. That was the alternative hypothesis for what this graph might look like. Okay, so the important thing is the design of this was quite good. He did systematic lesions. The data seemed very reliable, and he came up with a law that was consistent with the data that he found. And for many years, in fact, for about 27 years after these seminal studies were shown, everybody believed that in the hypothesis that, in fact, memory is not localized. Memory, well, vision, it's not like they didn't understand, oh, well, I know vision happens in the primary visual cortex. But memory was different. It was a higher cognitive function. So it wasn't unreasonable that you might need a whole network of brain structures, large amounts of cortex, to do this processing, and it's doing it in this kind of group dynamic kind of way, so that little lesions in any part wouldn't be a problem, but large lesions really takes out all of this higher cognitive function. So this was a reasonable idea backed up by data from a very famous Harvard psychologist, and it was the idea of the time. It turns out to be completely wrong. And the cool thing about the memory, learning and memory literature is that we can pinpoint the birth of what we call the modern study of learning and memory with the publication of a single paper. It was a publication of a paper in 1957 by these two researchers, William Scoville and Brenda Milner. Scoville was a neurosurgeon, and he was involved in what's called psychosurgery. Have anybody seen the old reels about frontal lobotomies that were done in the 20s? And so the idea was that neurosurgeons were trying to go in surgically and cure neurological diseases by making lesions. And what they ended up doing is they might calm a very disturbed psychotic patient, but they were basically cutting off the frontal lobe from the rest of the brain, and they became vegetable-like. It was not a cure. This was experimental brain surgery on patients. Now, one form of brain surgery that was helpful, effective, and did not cause long-lasting impairments in the way that was usually done was neurosurgery for epilepsy. So epilepsy is one of the most common neurological disorders still today. And way back here in the 40s and 50s, they knew that the structures of the medial temporal lobe, in particular the hippocampus, was a site of epileptic seizures. So the epileptic seizures start in the hippocampus. It's very what we call epileptogenic. It's easy to generate a seizure right there. And what they found is that if they went in and damaged the hippocampus on the side that was starting the seizures, you can almost cure people with very, very severe epilepsy. So that was very useful. And that was another kind of surgery that these psychosurgeons like William Scoville were doing. Okay, but they were doing lots of things, again, trying to cure schizophrenia and epilepsy with neurosurgery. Brenda Milner was a neuropsychologist, and I will tell you what her role is today. So this is the famous citation, Scoville and Milner, 1957. And it has to do with the description of a particularly severe amnesic patient who happened to be an epileptic patient under the care of William Scoville. The patient whose initials were HM, and for many, many years, from 1957 until 2008, he was only known by his initials while he was still living. Patient HM. When he was age of 7, he sustained a head injury involving a bicycle. He experienced his first major seizure at age 10 and first generalized convulsion at age 16. And between the age of 16 and 27, his seizures got more and more frequent and more severe. This was the level of epilepsy and the level of seizures that he was having every day made him not be able to work. He couldn't hold a job. He couldn't go to school very well. This was a debilitating kind of epilepsy, and it was not treatable by any drugs that they had at the time. So because of that, he became eligible for surgery to try and alleviate his epilepsy. But his epilepsy was so severe that Scoville here decided, and with the permission of both HM and his parents, I think he was 27 at the time. Yeah, he was 27 at the time. Patient HM was 27 at the time. Decided that the epilepsy was so severe that they were not just going to remove one hippocampus on one side of his medial temporal lobe, but they were going to remove both at the same time to make sure that this very invasive surgery would actually do the job. Okay, and so that surgery was performed when he was 27 years old. Well, the good news was he woke up from the surgery. He survived the surgery just fine. Scoville was a very, very skilled neurosurgeon. He woke up just fine, and his epilepsy was much improved. It was not completely cured. He still had to be on medications, but with medications, his epilepsy was much improved. But it became clear immediately that something was very, very wrong. HM could not remember a nurse that came into his room not 2 minutes ago to ask him something or give him some food. He could not remember what he did, whether he had breakfast that day. He could not remember any of the things that he was experiencing during the day and be able to tell you if more than 5 minutes passed. When he talked to you, he said that it was like waking up from a dream at every moment. It's like, okay, now I'm awake. Now I know what's happening. And he could appreciate everything going on. He would be able to have a conversation with you and be able to appreciate the weather outside. But once that immediate conversation left his consciousness, he would have no memory of it. So this is one of the reasons and one of the cases that made all of us appreciate why this particular system that was damaged with this lesion is so valuable. Because the memories of our everyday lives and our experiences, if you think about it, it really helps form our own personal histories. Think about it for a second. Would you be the same person if you didn't have your memories for the last 2 years? You're the same person, but okay, so he's saying no. Anybody think they would be the same person if they didn't have all of their everyday memories for the last 2 years? So this is what happens. You take away the patient's ability to form any new long-term memories, any new elements that make up your personal history. It was devastating. The good news was that he could still remember his parents. He could remember growing up. He could remember his schoolmates. He could remember all the things he learned in school. So he had a good knowledge. In fact, his IQ went up after this surgery, mainly because it was so devastating to be having these seizures and micro-seizures when he was trying to take the test. So he maintained that level of knowledge, that a good part of it was gained through his schooling, so that was still accessible to him. But from the day that he had surgery, he was no longer able to put into his long-term memory any new information about the events that happened in his life or to be able to learn new facts, okay? So all of the things that came into being after the surgery in 1953. So the surgery was performed in 1953. The paper was published in 1957. Computers, he lived until 2008. Computers, completely don't know what it is, can't learn about it. He can be shown how to do it. But all these things that came, all the presidents that came after, if you'd asked him who the president is, he would say he's heard of John F. Kennedy, but he would have no idea of any of the presidents that that took office after he was 27 years old. Okay, what did they take out? They took out his hippocampus and his amygdala. They weren't trying to take out his amygdala, but what they did is they went in frontally. So they actually did a big craniotomy up here. So my frontal lobe is right behind my forehead here. They lifted up the frontal lobe to look down on the temporal lobe. And they went through the cortex, through the amygdala, to get to the hippocampus. And they did that on both sides. What section is this through the human brain? Coronal. And what about this? Sagittal. And what about this? Horizontal. What structure do you think is highlighted in red here? Any guesses? If you read the top of the slide, you might get a few guesses. Hippocampus. Okay, hippocampus. Who remembers what the sheep hippocampus looked like? Who dissected out the sheep hippocampus? Anybody? No? Did you have a picture of the sheep hippocampus in your atlases? Okay, some tentative yeses. So the hippocampus is a long tube-shaped structure that sits in the bottom and the medial aspect, close to the midline of the temporal lobe, okay? So this is the full kind of anterior-posterior extent of the hippocampus. It's approximately 10 millimeters, 10 centimeters long in the human, sitting down in the temporal lobe. In the coronal section, you're seeing the two hippocampi cross sections right here and right here. You can see how far medial it is. Here is the temporal lobe right here. Here is the parietal lobe. Parietal lobe up here. This is the thalamus that you all look like. So we're cutting through the hippocampus at this level. We're seeing it right here. And then this is a horizontal section, looks like this, cutting through, and we're seeing part of the hippocampus there. The amygdala, which was also damaged in patient HM, sits, where does the amygdala sit relative to the hippocampus in your brain twister experiment? Where was the amygdala person relative to the hippocampus person? Anybody remember? Anterior, sitting right anterior. So, but the amygdala is a little ball. And this isn't the best plane to see it, but the amygdala sits right here in a little almond-shaped ball. Amygdala means almond. It's almond-shaped, so hippocampus is cigar-shaped. Amygdala is almond-shaped. It's sitting right here. The neurosurgeons, William Scoville, came in through here. Here's the eye, lifting up the frontal lobe in front of the eye, and went through with his cauterizing electrode, cauterizing implement, went through the amygdala here to damage what he thought was about 8 centimeters of the 10 centimeters of the hippocampus. He left a little bit of hippocampus in the back. Yes?
Did they do tests on HM to see whether or not he still felt fear?
Yes, they did. And his affect was blunted, was definitely blunted. But the most devastating, I have to say, and the most obvious impairment he had was the memory immediately. Okay, this is an illustration from the original paper published in 1957 where Dr. Scoville is showing the 8 millimeters that he believes he took out visually from the tip of the temporal lobe where the amygdala sits all the way back. And this is a drawing of what he thought he took out, where this side of the brain, these are coronal sections again, shows you the anterior part. Here is, he called it the uncus. This is just anterior to the hippocampus and the amygdala. This is all taken out. Here is intact on this side and what he thought he took out on this side. So here's the anterior hippocampus completely taken out. And here's more posterior hippocampus completely taken out. Again, a little bit of hippocampus left taken out here, but there's still hippocampus that he felt that he might have spared there. Okay, and here is actually an MRI image of patient HM. There was a really interesting story about why HM wasn't imaged for such a long time. And the story was that they put surgical clips on his arteries within the medial temporal lobe during surgery to stop the bleeding. And the thought was that those clips were ferromagnetic so that he could not go into an MRI magnet. So you know that when you go into an MRI magnet, if you have a pacemaker, you can't go in because it'll screw up the pacemaker and then your heart will stop working. And you know, all your credit cards, if you have the credit cards, will be damaged. Well, obviously, you do not want an arterial clip, a metal arterial clip in your head when you're being imaged. And so that it was thought that that was not possible for him to be imaged. But it was actually a journalist who was examining this and said, actually, you know, this is such a historic thing. We want to be able to look at his brain while he's still living to see how accurate Scoville really was, because so many studies had been done at this time. And so the journalist ended up going to research the company that made the clips, from the clips that were being used at the time that HM got his surgery, and he confirmed that, in fact, those clips were non-ferromagnetic. So because of this journalist, they said, okay, well, oh my gosh, I always thought the clips were ferromagnetic, but he confirmed they were not, and they successfully imaged him. And so you're able to see, this is a normal brain right here, hippocampus on both sides, and you can see a lot of the cortex is done. There's a little snippet of tissue right here where the hippocampus used to be. And this is the cerebellum in a similar slice. And the cerebellum is also very degraded in patient HM. Why? Because the anticonvulsive drugs, anti-epileptic drugs, I should say, that he was taking, is damaging to the cerebellum. So we were able to confirm the damage in the patient HM while he was living, as well as see how much of his cerebellum had been damaged, which wasn't fully appreciated before. But what were the major findings from patient HM? The first major finding was taken from the observation that his IQ was actually improved. He had normal IQ, but he had this devastating memory impairment such that any new information did not seem to be able to go in. Also, I should say that his personality was completely intact. Same sweet guy, but no memory. So major finding, memory could be impaired selectively without loss of other cognitive functions. Second major finding, Lashley was wrong. There is one specific part of the brain that you could damage to get very, very selective and devastating memory impairment, and that part of the brain is the general area of the medial temporal lobes, okay? But as I said, the damage was specified in terms of an epileptic surgery, but multiple areas were damaged. They damaged the amygdala on both sides. They removed the hippocampus, most of the hippocampus on both sides. And part of the cortex surrounding it that you had to damage just to access the hippocampus and the amygdala were also damaged. So if you read the classic paper, Scoville and Milner proposed that they thought that the hippocampus was probably the key structure. But they could not be sure because of this other damage. They couldn't be sure that the impairment was not due to combined damage of the hippocampus and the amygdala. And so the localization of what was causing this really striking memory impairment was not absolutely clear. Okay. So I have two key terms to introduce, and we're going to start building up a list of what is spared and what is impaired in damage like patient HM. Oh, sorry, let me just emphasize one more thing before we get there, and that is I've been telling you that William Scoville did the surgery. That was his job. He was a neurosurgeon. But the one that made all of the what we call neuropsychological assessments, the memory assessments, and tried to link it to the parts of the brain specifically, was Brenda Milner. Brenda is in her 90s now. She's still working at the Montreal Neurological Institute and is really credited to be one of the really pioneers in memory research. It was her careful research and careful assessment of HM that really put us all on the right track to being able to study in a very specific way parts of the brain important for both learning and memory. So it's her work that I'm going to be focusing on in the next part of the talk. Okay, key term, anterior grade amnesia, okay? So let me just dispel something. Amnesia is not what you see in the movies, unless you look at the movie on the list for your movie assignment, which is Memento. Anybody see the movie Memento? Okay, very, very cool. So his memory impairment is depicted well, but if you remember, he slipped on the bathroom floor and became amnesic. I'm sorry, that does not happen. You become amnesic with medial temporal lobe damage. So amnesia is loss of memory, and we're going to talk about what specific kind of memory is lost in amnesia. But anterior grade amnesia refers to inability to form new memories from a particular time point. HM suffered from severe anterior grade amnesia from the point of time in 1953 when he got his surgery. Anterior grade amnesia, severely impaired, or he exhibited severe anterior grade amnesia, okay? Retrograde amnesia refers to loss of memory for information acquired before the event. So did HM have retrograde amnesia or not? No, he did not, because I told you that he could remember his parents, he could remember his home, he could remember his neighborhood, he could remember his friends from school, he could remember his teachers. However, he had what we call partial retrograde amnesia, because if you look far back, so he was 27 when he got this surgery. He remembered his parents, of course, they've been with him all his life, and his teachers from grade school and all of his friends. But if you question him carefully about the several years leading up to the surgery, his memory was impaired. So long-term, very long-term, well-established memory was spared. But memory that was acquired in the last few years before his surgery was still impaired. So he had partial retrograde amnesia and partial sparing of that information before. We're going to talk, that's a very, very interesting and important point. We're going to talk about what that means. Yes?
So you're saying that you can't get amnesia from any kind of accident, it has to be actual surgery or surgery?
No, that's a good point. So he asked, do I mean that you can't get amnesia for any kind of accident and it has to be surgery? No, it does not have to be surgery, but to get real amnesia, you must somehow get damage to your medial temporal lobes. And that usually doesn't happen in a fall. It can happen with traumatic brain injury where you happen to get that, but that's usually happening damage together with lots of different things.
So it's not just like it has to be removed, it can be
No.
damaged.
No, it can be damaged, and what can happen is the hippocampus, sadly, and these medial temporal lobe structures are very sensitive to ischemia, lack of blood and oxygen to the brain. And so what happens is patients that go into open heart surgery, where the blood to the brain can be compromised a little bit, actually many of them tend to come out with memory impairment. They may not be severe, they're certainly not severely amnesic like HM, but that does cause enough damage to these very sensitive hippocampal cells that you start seeing clinically visible memory impairment. So these hippocampal cells are very special. They're epileptogenic, they're very, very susceptible to epilepsy in general, and they're very susceptible to lack of blood and oxygen. So if you have some ischemic event, you know, what's it called, a sea diving, scuba diving accident, and you don't get oxygen for a while, it's your hippocampal cells that tend to die first, and that causes memory impairment on your road to amnesia. Okay, so we have anterograde amnesia in patient HM. What's impaired is memory for all information acquired after the onset of his surgery. And we have a mixed bag for retrograde amnesia. He only has a partial retrograde amnesia for information right before his surgery. By right before, I mean a couple of years before, but very good memory for early life, very well-established long-term memories. This means, particularly this anterograde amnesia that he exhibits, means that the medial temporal lobe is critical for the initial formation, what we call encoding of new memories. But it is not the place where well-established long-term memories are stored. How do I know that the medial temporal lobe is not the place where long-term, well-established memories are stored? How do I know that? Yes? They'd be gone in HM, and I told you they're spared. So they cannot be living long-term. There's some sort of neural signature that lives in your brain that helps you remember your grandmother, okay? That is not in your hippocampus, because even if you were to have hippocampal damage right now, you would still remember your grandmother. You would still remember your mother. It's not there. It's someplace else. It lives someplace else. We're going to talk a little bit about where that is. Okay, so very sadly, at the age of 92, after living first with his parents, and then after his parents died, he had to live basically in an assisted living facility. HM died on December 4th, 2008. There was, and we all learned his real name. He was Henry Mollison, and he probably is, and for a long time will be, one of the most studied neurological patients that ever existed. From the time in the 1950s when he was first described until close to his death, they continued to study him and ask, can he learn anything? What if I teach him this way? Can he learn that way? Continue to participate very, very willingly because he did recognize he had a memory impairment. He knew that. And he was very, very gracious in knowing that he could probably help somebody. So he was very open to all the testing that had been done with him for basically all of his life. So I told you that there was anterograde amnesia, partial retrograde amnesia, and I told you all about what his impairment looked like, particularly to Brenda Milner, who first described him. But the question was this memory impairment global, or were there certain things that HM could learn if you asked him in the right way? So what else could HM learn and remember? And one of the many fundamental pieces of information that Brenda Milner identified in patient HM is that there are certain classes of learning and memory tasks that HM could perform completely normally. Many of these tasks were kind of motor skill tasks where you show your knowledge, not by verbal conscious recollection, but by actually a motor performance. And one classic task, the first task that she identified, was a simple task called mirror tracing, shown here. So here, you're using your preferred hand, and you have a star, and the star has kind of double lines around it, and you have to learn to trace in the middle of those lines all the way around, which would be fine if you had the paper right in front of you, but you actually have to do it looking at the mirror. So you have to coordinate your hand and get your hand to move mirror reverse and stay within the lines. It actually takes quite a while to get good at it, and your time, your reaction time, your speed to get through the star gets better, and your accuracy gets better over time. But it takes, I don't know, 16, 18, 20 different trials for you to get really, really good. So they did something pretty amazing. They discovered something pretty amazing. They put HM in front of this. They told him what to do. He understood the instructions. Again, he has high, an average level IQ. And he did several trials. Did a trial, do it again, do it again, do it again. By the end, he looked at it and he said, wow, I'm good at this. And in fact, his scores had improved. He is getting right in the middle of the line. He's doing faster than he's ever done before. And we asked, Henry, do you remember all the 20 trials that you did to get faster? He said, no. This is the first time I've done it. I've never done this before. So he had no conscious recollection of actually doing all these trials. They were spaced out over days, but he did, I don't know, 10 trials a day. But you can see the learning and the motor skill being expressed, even though he didn't have any conscious awareness and conscious access to that information. Here is his performance, just to show how good he was. 10 trials a day for 3 days. Getting better, they made sure he remembered the rule, kept reminding him of the rule, so that he knew what to do. Day 1, day 2, day 3, he is a pro. He's doing this so fast. And on this day, he says, wow, I'm good at this. And they said, yeah, you are so good, but you did it for 3 days in a row. And he has no recollection. He said, no, I didn't. This is the first time I remember doing it. So that is the kind of world that he lives in. Let me give you another example of a kind of motor skills kind of task that he was able to do perfectly well, as fast. Oh, let me just make this point, that this learning curve is just as good as you and I that have completely normal hippocampi. The only difference is we would be able to remember day 1 I was doing badly, and all the different events associated with these days, and we would get better. Yes, question. How did he remember he had a disease? He knows consciously that he does not have a good memory. Why? Because he knows that he could remember some things. He has memories from his parents, and again, his IQ is normal. In fact, he was able to learn how to cover pretty well for his memory impairment in general conversation. Just like we all, I mean, haven't you had a conversation with somebody who you can't remember their name, but you're supposed to? Do you know how to cover for that? Yeah, I'm really good at that too. And so HM learned that. So he had that again, he has a normal IQ. He just cannot put new things in long-term memory, okay? So it's kind of mind-blowing to think about this. Yes?
Does this mean that like muscle memory is not connected to like your recollection?
That's right. Muscle memory is done by separate substructures. And if you ask me what these structures are involved in, this type of learning, it would be the extramotor, extrapyramidal structures that we talked about. Structures like the basal ganglia and the cerebellum are very important for this. If you have damage there, you have a much slower learning curve. You don't have the coordination or the memory to remember this. But you can do this perfectly well because his basal ganglia was perfect. Cerebellum wasn't so bad, but you can, he did perfectly fine. No different from normals. Okay, second example, backward mirror reading. Okay, again, really hard to do if you practice reading text that is mirror reversed. I mean, it takes me a long time. But if you practice, you actually get really good at doing that. Same kind of thing. You see the same improvement in HM. He read faster and faster. His reading's fine. He could read just fine. He learned that before his accident. Has no memory for having practiced it, no idea why he's pretty good at it. He just thinks, oh, hey, I'm good at this. Okay, so now we have something new to add to this list of spared and impaired kinds of performance. Severely impaired anterior grade amnesia. But now we know that anterior grade amnesia, this kind of memory impairment, is only for certain kinds of memory. That form of memory, again, this is again why Brenda Milner is so well respected in the field, is that she helped identify that this form of memory that HM was so impaired at was conscious memory. We call it declarative memory, memory that you can declare, okay? Can you tell me your favorite vacation ever? Okay, your favorite Christmas ever. Okay, great. You went to Tennessee way back. How many years ago was that?
At least 10.
Okay, 10 years ago. Great memory for these kinds of things. But this is a memory that you can consciously recall. Do you remember details about that trip?
I took my hat and threw it over a cliff.
He took his hat and...
On a rock instead of the river.
Okay, he took his hat, threw it over a cliff, and it landed on a rock instead of a river. That is a perfect example of what we call a declarative memory, something that you could pull up from the past. It has details in it. It brings up the personal experience. You probably remember what time of day it was, maybe information about who was with you. This is the kind of memory that is impaired in HM, and that's the kind of memory that forms your personal history. That's part of you now. You have this great memory of that vacation. That's what's lost in patient HM or in other amnesic patients. They can't form those kinds of memories anymore. They're lost. They can experience them, but they have no memory of them anymore. Okay, so that's what we're referring to in anterior grade amnesia or memory impairments for this kind of consciously recalled, I'm going to call it declarative memory. Retrograde amnesia for the same kind of information is partially spared. We talked about that. But now we know that also spared are what we call motor procedural memory. These examples that I gave you, mirror tracing and backward reading in a mirror, are categories what we call non-declarative memory. Memory that's not, you can have conscious recollection of this experience, but you don't have to have it to actually express the memory itself, okay? So this is called non-declarative kind of memory. Now don't get confused. I'm not saying that there's no declarative information about these learning situations. You do have declarative memory about these individual sessions and information about how you did on the sessions. But being able to express it itself is non-declarative. You do not need your medial temporal lobe, okay? So this is what I want you to understand about our understanding of what happens when you have damage to the medial temporal lobe. And now what I want to do is give you a clear example of what this actually looks like in real life. So patient HM unfortunately passed away. He was 82. He was very, very protected. Nobody knew his name. Nobody knew where he was. He had very limited access to only a few people, because if everybody knew, then all the neuroscientists would rush him and try and test them for their own experiments. That didn't happen. What we're going to see is an interview with an amnesic patient that ends up having very, very similar damage to patient HM. This patient did not undergo this bilateral surgery. Oh, I'm sorry. One very important aspect that I meant to mention is that one of the reasons that Scoville and Milner wrote that paper was not only to say, oh my God, look at this cool memory finding that I got, but it was to say, you cannot ever do this kind of epileptic surgery again. We know that that damaging one hippocampus can both alleviate epilepsy, and you have small memory impairments, but you're still functioning. You take out both hippocampi, as we tried to do experimentally. We didn't know what was going to happen. You're going to devastate your patient for the rest of his life. HM could not work. He could not function on his own. So this was a warning to other neurosurgeons that it cannot be done, because it's devastating. And I mean, the good news is not for HM, but we discovered something very, very fundamental about the brain, but at a very, very severe price. Okay, so we're going to be looking at an interview of patient EP. EP suffered from encephalitis, which is a viral disease that affects both parts of the brain. And usually encephalitis patients have very, very messy lesions. Hard to study them because they have damage different on one side than the other, and it's really big on one side and small on the other. But EP had encephalitis that happened to damage exactly in the same lesion spot where HM had his damage. His medial temporal lobes, and only his medial temporal lobes, are quite limited to the medial temporal lobes, were damaged on both sides just by chance. So he identified as an amnesic patient. He came in to be studied at UCSD by a very famous neuropsychologist named Larry Squire, who you're going to see. And we're going to be able to see some of these major characteristics. You're going to see examples of his anterograde amnesia and his spared retrograde information, his spared long-term memory. We're really not going to see his spared procedural motor. That's not on the interview. This was a Scientific American interview that Alan Alda did with EP, Larry Squire, and Larry Squire's wonderful technician, Jennifer, who is going to be doing the testing in EP. So let's take a look at that. Sorry, Ellen Alda sounds like a chipmunk, but I can't help it.
Do some work again. EP is now 82. In 1992, retired from a career in electronics, he suffered an acute virus infection that destroyed part of his brain.
Research and development, that's what I like.
Most of his thinking skills survived the damage virtually intact.
Why should people pay taxes?
To support their country and their counties and states to pay for things.
If you were lost in the forest during the day, how would you go about finding your way out?
I would find a river and follow the river down to wherever it may go. Mm-hmm. Ocean, lake.
EP can also copy complex drawings.
That it, huh?
And he not only has no difficulty repeating back a list of words, In this case, dog, raccoon, lion, and parrot.
Dog, raccoon, lion, and a parrot.
Good.
But he even has a little sly fun with Jen along the way.
What you gotta add is about 2 more.
Oh, really?
Then
Would that make it tougher?
Then that would catch them. 7, you know. Leaf. Medicine.
EP really hits his stride when the testing of his cognitive skills involves Jen's laptop computer.
Gold. Having been in electronics over the years, I am amazed at all this. It's just wonderful. Believe me, little printed circuits, just, oh, you can't believe it. It used to be in a 6-foot rack, and down to this, it's just wonderful. When I was in electronics, this would be in a 6-foot rack.
But it's now that something odd about EP's behavior becomes apparent.
Printed circuits, diodes, triodes, and all that stuff in there. Oh, it's just amazing, believe me. When I was in electronics, this would be in a 6-foot rack. This would be in a 6-foot rack. It would be in a couple 6-foot racks. It would be in 6-foot racks. This would be in a 6-foot rack. And now look at it, down to this. Little printed circuits and...
So he's not aware that he's told us 3 or 4 times that he used to be in electronics, that a computer used to fill a room, and that now it's down to the size of a microchip. He's just not aware that he's said those things several times.
No, he tells us the same stories again and again. We've heard these stories before, and we'll hear these stories again.
the equipment that it takes.
How was it? How have you been? You've been enjoying this?
Oh, I
session?
enjoy this.
Yeah,
Absolutely.
It is interesting.
It's-
Isn't it?
look at the work you guys are doing. You're getting wonderful, I believe.
I'm sorry, I forget her name. What's her name?
Her name?
Yeah,
I don't remember.
Okay, Jennifer.
Jennifer.
Jennifer. Yeah.
I'm sorry.
Have you
Oh,
have you met Jennifer before today?
I think so, yes. I'm not positive, though.
Yeah.
I'm sorry, my...
No.
Oh, that's
It's
okay.
okay.
We all have.
Well, we all get that one.
Oh, sure. How much have you worked with him?
We have probably visited his house 200 times.
200 times. And for him,
200
is
times.
each time
You
the
can't
first
remember
time
her
for
name.
him?
Well, you see, it's yes and no. It's clear that he does have a record of the experiences that are based on the habits, the interactions, the emotional values of the interactions, the fact that they've been positive and not negative. He certainly lets us in the door faster.
I mean, like you saw, he couldn't tell you my name.
Yeah.
He couldn't tell you if you saw me before. But there's definitely a rapport there that I think has been built, and he's aware on some level. I read you some words about 15 minutes ago. 4 of them. 4 words. Do you remember me reading you 4 words?
No, I can't
No?
recall. I'm sorry.
No, that's okay. Don't need to
My
apologize.
mind is getting old.
That's okay. I read you 4 animals, and I want you to tell me yes if you think the animal was on the list I read you about 15 minutes ago, or no if it was not on the list.
Wonderful.
Okay? Cat.
Yes.
How sure are you?
I feel reasonably sure on that
Reasonably
cat.
sure? Uh-huh. Raccoon.
No, I feel no.
Giraffe.
Yes,
How sure are you that I read
I'm
you
real
that?
sure on that.
Real sure?
They're beautiful animals,
Okay.
believe me.
Lion.
No.
Okay.
EP's inability to remember things that happened just a few minutes ago can be traced directly to the damage the virus inflicted on his brain a decade ago. The areas destroyed were in his temporal lobes, most critically a structure called the hippocampus and the brain tissue immediately around it. Without a hippocampus, EP lives in a permanent present. Anything new that happens to him simply doesn't get recorded.
Do you remember drawing something for me today?
No.
Drawing something about
No.
15, 20 minutes ago?
No.
Remember picking- Okay.
I'm sorry.
Don't apologize.
Yeah.
Thank you for trying. Thank you.
But although EP can't record new memories, old ones from the years before his hippocampus was destroyed are remarkably intact.
Hayward.
He grew up in Hayward, California.
How about your house on Castro Valley Boulevard to the Hayward Theater? Do you remember where the Hayward Theater is?
Yes, I would leave the house and turn to the right to A Street, down A Street to Castro Boulevard, and turn to the left.
Okay. So I think that's a really striking example of what I was talking about. And it's hard to imagine. I mean, it's one thing to listen to it in lectures, but it's another thing to actually see somebody suffering from amnesia. So tell me, what were some of the examples that you saw of his impaired anterograde amnesia? What couldn't he do? Yeah? Right, he couldn't remember the animal names. So, you know, with a delay like that, you and I would be able to easily do that. That is the kind of, so this is an example of factual information that we come in, maybe not so your example was what we call an episodic memory. Memory of an episode. Those things are not able to be encoded in patient HM. But the other thing that's impaired is memory for facts. And the words that he described were also an example of the facts or semantic memory. Any other things that you noticed? Yes? The location of his own home. So I could probably find out how many years he had been living in that home and the streets. But I imagine that it's, you know, maybe he could have even moved there several years before his surgery and unable to remember. So that means that he can't be let out on a walk by himself because he could be completely lost even though he lived there for a long time. Yes? Right. So the question is, if he lives there and he goes around the house and he goes around the neighborhood, can't it sink into his implicit memory, not his declarative memory, but his implicit memory? And the answer is that something as complex as his house and street names and directions will never get into any kind of memory. He may have some feeling of familiarity, but this is still very dangerous for him to go out because he'll go, who knows? But that's an interesting question about his house, his internal house. I don't know how familiar he is. I think I do remember that they did a test, asked him to draw the layout of his house that he's living in, and I have a feeling he did not do very well. So again, he's comfortable there. He feels like he's at home, but when asked details, to pull out those more conscious details to make an explicit map, very poor. I mean, you know, if you go to the hotel room, does somebody need to show you where the I mean, it's not a mansion. So, but that's a good question. I don't think that was a problem. I don't think he needed supervision for that kind of stuff, but could not go out anywhere on his own. Yes?
What if they sort of did sort of like a maze type thing where he had the same starting point and the same ending point every single day
Yeah.
for many days?
Yeah.
Would he be able to rewalk it alone at some point eventually? Or the same every day?
Yes, that could be a possibility, but it would have to be very, very well controlled. So in fact, they did this in rats. So you actually just came up with this classic rat experiment to differentiate a hippocampal dependent task where they have many more possibilities to figure out versus a striatal dependent task where they can learn one route. I go 5 steps here, 5 steps here, 5 steps here, and rats with hippocampal lesions, but with spared striatum can do that. Did they do that? No, because it's still too dangerous and they needed to be with him anyway. But that is theoretically a possibility. Okay, so, before we move on, we talked about things that he was impaired at. What did you see that he could do? What could he remember? Yes?
He could copy
He could copy
a drawing.
a drawing. Did you remember that drawing later? He couldn't remember drawing it. So he had the motor skills to copy a complex drawing. Perfect. Any other examples? Yes?
He had vivid memory from like the geography of where he grew up.
really striking. That was a science paper that they published on him, that they actually had to go back to 1920 Castro Valley and find the original streets and the original city plan and tested him explicitly. He was amazing. I mean, I don't remember that much about my hometown, so hopefully I don't, well, they would never do a science paper on me. Was there another question? Did you have a question? Yeah.
I was just going to say that he kept repeating certain things.
Yes. Yes. He kept repeating certain things. And if you have people that you know that are more elderly that tend to do that, it's because their memories, their declarative memories just don't work that well. Yes?
The thing that I thought was really interesting was it wasn't just that he would repeat the same thought multiple times, it was almost the wording
Yeah.
of his thought was exactly the same every time.
Right, right.
Which was something that it wasn't just that he couldn't remember saying it, it was that he had this thought in his head that, I thought that was really interesting.
Yeah, so he had this thought in his head that kept coming out. But it came out appropriately. He was cued by the computer, and he continued to be, amazed by the computer, and that triggered this memory. But he certainly didn't remember. If he had known he'd said it 5 minutes ago, I'm sure he wouldn't say it again, but he had no memory of that. Yes?
So are memories like that are linked to certain smells? Are they stored in long term, or are they stored somewhere totally different?
So the question is, are our memories that are linked to smells, where are they stored? Are they stored in the hippocampus? Are they stored someplace different? That's a really interesting question. So smells have kind of a privileged route to the hippocampus, because vision has to go through V1, V2, all the way down through the temporal lobe and finally gets projected to the hippocampus. Olfactory information has 2 synapses to get to the hippocampus. Very, very fast direct projection, which is why smells can be so evocative of particular memories. Your mother's, whatever, apple pie, it has a particular smell. I think those smells, again, are I don't think they're stored in the hippocampus. There's not a lot of information that is actually stored in the hippocampus. So like other memories, those smells and those memories are stored from other areas, but they get perhaps encoded or consolidated or strengthened even more profoundly because of this fast access that olfaction has to the hippocampus. Any other questions? Yes?
I understand that he couldn't remember Jennifer after 2.5 meetings.
Right.
But why was he able to open the door faster when they knocked?
Yeah.
Is that procedural memory?
Yeah.
Or is that
Yeah. So that's a great question. So he said, I understand why he couldn't give Jennifer's name, but how come he has this familiarity with her and feels comfortable with her much more after time 200 than he did the first time, when he might have been much more, Larry Squire said that he opens the door much faster. And again, this is because this is showing precisely the specificity of the impairment that he has. Other brain areas, including the amygdala, which is partially damaged, probably not fully damaged, can help you remember the feelings that somebody evokes to you. Even though I don't remember your name, it's like, oh, you're familiar. In this spot, I'm familiar being in this kind of situation where I'm speaking to lots of students. You guys look like students, so I feel familiar, even though I might not be able to tell you the last time I gave a lecture, what I gave a lecture on, or any of your names. I can still feel familiar. And that tells you that that kind of plasticity, memory for that information is someplace other than the medial temporal lobe. And that's the cool thing about this. This is very, very specific. And next time we will go over all of the different subdivisions of this type of declarative and non-declarative memory. So see you on Monday.